In this chapter, we're going to talk about hypothesis testing for one population mean. I want to introduce the main ideas in this chapter with a single example. And so the example is going to say that we're going to suppose that we're a medical researcher and that we're trying to determine whether or not a particular drug is effective at treating a certain fictional illness, which I'll call spontaneous dental hydroplosion or SDH. A researcher finds that the mean duration of SDH is 7.5 days, and that's if the patient receives no treatment, if the drug is not offered. And then there's a treatment group. So there's a group that gets the drug, and they find that the mean duration of the illness for that group is 7.1 days, with a sample standard deviation of 0.7 days. And so what we want to know is this enough? Is this information enough to determine that the drug has an effect on the mean duration of the illness? And so what we're going to do to determine whether or not this is enough information to determine the drug has an effect is we're going to run what's called a hypothesis test, naturally. Okay, and so what we're going to do is we're going to set up what's called the null hypothesis. The null hypothesis is the idea that nothing happens. Okay, so in general, the null hypothesis means nothing happens. In our context, it means that the drug has no effect. And so the null hypothesis is going to be the hypothesis that the drug has no effect. In other words, the mean of the patients that receive the drug is actually still 7.5. And here the idea is that we have some data set that's normally distributed. Okay, so we have some data set that's got a mean of 7.5. We're assuming that our data is normally distributed. And maybe it's possible that we just collected the data, we grouped together all the patients that were on this side of the chart, right? So maybe when you look at that, the mean is 7.1 just by the fact that, just by chance, you happen to get that group of people with a mean of 7.1. How do we know whether or not it's really the medicine? And so that's kind of the question that we're going to answer is, how do we determine the threshold? How do we determine the threshold that it's actually the medicine and that there's some effect rather than it's just kind of a random chance that this happened? So that's really what we're going to concern ourselves with this chapter. And there's different aspects to this question. There's different methods that we're going to use to solve it. And so we'll talk about all the details as we go along. But the main idea is that we just want to check, does this drug have an effect or not? Okay. So the null hypothesis is that the drug has no effect. In other words, the mean is 7.5 days, whether or not you have this particular drug for the illness. The alternative hypothesis in general is that something happens. So in this case, the alternative hypothesis would be that the drug actually shortens the mean duration of the illness. And so we can write that as that the mean is actually less than 7.5 under having the patients take medication for this. And this is it. This is the null hypothesis and the alternative hypothesis. I will show you there will be some formulas that we can use depending on how many patients we have and how the whatever the mean duration is and all the different statistics that we can collect. And so all the data that we're going to have is going to tell us, do we have enough evidence to say that the drug has an effect or not? Okay. And I want to be careful about the way that I even say this. That really is going to be how we answer the question or how we think about it. Do we have enough evidence that the drug has an effect or not? Okay, that doesn't mean that the drug has no effect. It's just we might not have enough evidence to reach that level to be sure that it's the drug rather than, say, randomness. So again, statistically, there's no way to know whether or not it's actually the drug that's shortening the duration of the illness or whether we're just randomly picking values that are below the mean, say. Okay, and so what we want to do is we want to tease that out somehow. We want to get to a certain threshold of figuring out whether we reject the null hypothesis or not. So let's actually write that out. We have two possible outcomes. Okay, so we have two possible outcomes. The first is that we can reject the null hypothesis. We can decide that we have enough evidence and we can reject the null hypothesis. And this is the idea that we're deciding that we have enough evidence to say that the drug actually does shorten the duration of the illness. Okay. I wanted to just quick correct this here. So this is just the word reject. So we're going to reject the null hypothesis. That's one thing that could happen. And again, if the data tells us to reject, that's how we'll decide there. Or we could fail to reject. Okay, and so by failing to reject the null hypothesis is basically our starting point. And what we want to know is, do we have enough evidence to move past that starting point? So in our case, the burden of proof really is on the maker of the drug, as it should be. We want them to convince us that there's enough of an effect of this drug that it's actually going to shorten the mean duration of the illness. And so I kind of think of this like in a court of law: you're guilty until proven, or you're innocent until proven guilty. You're never you go through the trial, you're either guilty or not guilty. You're never ruled innocent. And hypothesis testing is the same, right? Either you reject the null hypothesis or you fail to reject the null hypothesis. We're not saying for sure we know that the alternative hypothesis is true or not. All we're saying is, do we have enough evidence to reject the null hypothesis or not? Okay, that's really it. Since we have two different outcomes, there's two ways to be wrong. So if we have two decisions that we can make, we have two ways to be wrong. Okay, so two ways to be wrong. The first is that we could falsely reject the null hypothesis. Okay, so in other words, maybe our data says, yes, there's enough evidence to say that the medicine actually works, so we're going to reject the null hypothesis. But it turns out later, looking back, that we were wrong about that. If we falsely reject the null hypothesis, this is called a type 1 error. Or we could falsely fail to reject the null hypothesis. So maybe we should have rejected the null hypothesis and we didn't, but we were wrong. So that's called a type 2 error. So type 2 error. Okay. So type 1 or type 2 error. And the way I like to think about type 1 and type 2 errors is false positives or false negatives. So what I mean by that is that type 1 error is a false positive, right? So the idea with the type 1 error, let me actually go back so you can see these at the same time. A type 1 error is where you falsely reject the null hypothesis, right? It's a false positive. In this case, the positive signal is that the medicine works. So we falsely have that positive signal. Or a type 2 error is you fail to reject the null hypothesis incorrectly. Okay, so again, type 1 and type 2 errors. The significance, which I'll call, come on, pen. So the significance, there we go. So the significance alpha is the probability. So the probability of making a type 1 error. Okay, so that's called the significance alpha. I just want to, at this point, contrast this to what we call the confidence in chapter 8. The confidence was 1 minus alpha. The significance is that alpha. Okay, so this is the probability of making a type 1 error. And what we have to do is we have to think of this as kind of a balancing game. If we let our significance be so small that we really don't make many errors, well then there's a lot of medicines that are going to work that don't quite meet that standard. And so we lose those medicines that have some pretty strong but not perfect evidence that they work. And on the other hand, if the significance is too high, if we have a alpha of say 0.5, what that means is that every other experiment, statistically speaking, is going to have the wrong conclusion. So if we were to run 100 trials and we had a significance of 0.5, then half of them would be wrong, right? That's clearly too high of a significance. Generally, what we do in the standard is to take alpha to be 0.05. So we have a 5% significance. So if we were to run 100 trials, we would assume that 95 of them are going to go the way that we want. Okay, so that's kind of the threshold. That's really the standard. And then different people might have different thresholds depending on what they're doing, right? Depending on, I mean, there's of course lots of things that we're not considering at all, including like side effects of the medicine, Really, we're just kind of thinking this is a black and white issue, right? We have either the medicine works or the medicine doesn't work, and there's no in between, there's no gray. So that's the significance, that's the probability of making a type 1 error. And so you want that to be small, but not too small, so that you get that balance, right? There's going to be two ways that we're going to decide whether or not to reject the null hypothesis or not. Those two ways are going to be using either critical values or p-values. So what I want to do first is to describe the critical value approach. And what we're going to do with our data is I'll have formulas that I'll show you on the next slide. And those formulas are going to tell us how do we compute our test statistic based on all of our data. So there's going to be a formula that we're going to look at. The formula will be a familiar one, actually. But what we have to decide is what's our significance alpha? How willing are we to be wrong? And based on that value of alpha, we have to look at our normal distribution and think about, if we compute our test statistic, are we going to reject it or not? So the critical value is going to be the value that's going to split the rejection region from the non-rejection region. The example that we talked about in the beginning, let's just zoom in on this for a second, was this one, where we just had what was called the left-tailed hypothesis test. And that was where we figure out the mean is what it is, or it's less than what we want. In our case, the mean was 7.5 or less than 7.5. These values have been standardized, meaning that you subtract the mean and divide by the standard deviation. So that's why everything is centered about 0. Okay. But what we're going to do is we're going to look at this data, and we wanted to know, is there enough evidence to say that our statistic is over here, right? And so again, we'll come up with a formula in a second, but we're going to compute that value, figure out whether it's in the rejection region or the non-rejection region, and decide accordingly. So a critical value is the value that splits the rejection region or the not rejection region. And this is important enough that I want to say it. Critical values, in other words, the values between the rejection and non-rejection region, our assumed critical values are part of the rejection region. Okay, so those are part of the rejection region. Okay. So that's really the critical value approach. We have a formula. We're going to figure out, based on that formula, is the value going to be in the rejection region or not? And then again, these are the cutoffs that we'll figure out here. So these cutoffs are the critical values. So this is called the critical value approach. You compute the critical value, and then based on whether it's a two-tailed or a left-tailed or a right-tailed hypothesis test, you determine, is your test statistic in the rejection region or not? And then that'll tell you what to do. If you do know the underlying population standard deviation, you'll use the z distribution, right, the normal distribution or the z table. If you do not know the underlying population distribution, we're going to use the t distribution like we talked about in chapter 8. Okay, so all the z's get replaced by t's, but otherwise everything else will be the same. Okay, same picture in same scenarios. So that's fine. So that's the critical value approach. The p-value approach is slightly different, but it's going to tell you the same information. The p-value of a data set is the probability that your data set is at least as extreme as what you get from your sample. In other words, it's the probability that the results that you're going to observe are at least as extreme as what you observe. So that's going to be the p-value. Okay. In other words, this is the probability that the value that you're getting is occurring by chance or not. And then you can compare the p-value to the actual significance alpha that you choose ahead of time. Okay, so that's going to be the p-value approach. We will do lots of examples, and I know that I'm throwing a lot at you here, but that's the basic idea. Okay, and in the link here, and I'll try and embed this link somewhere, there's a nice video about p-values that I've included there. Okay, so I will try and get a hyperlink here so that you don't have to copy that verbatim, but if you want to get at it right now, that's the link. Okay, so again, just a link about p-values and a general overview there. All right. By the way, I don't know why our book does this. This drives me a little crazy, but p should not be capitalized. Okay, so the p-value, when we talk about p-value, it should be a lowercase p. I don't know why the book used an uppercase, but I will stick with lowercase. And yeah, so that's p-values. So the way that this is going to work is that we're going to use all of the information that we've gathered so far, all of the formulas. These are formulas that are going to be available on our formula sheet that's on Canvas. And here's how this is going to work. Basically, there's going to be 3 types of hypothesis test. You can do what's called a two-sided test. You want to figure out whether the mean has some certain value or not. The left-tailed test, which is the one that we started with our medical example, maybe you want to know that the mean is equal to some value, or you want to know whether or not it's less. Or the right-tailed, right? You can figure out that the mean is what you think it is, or maybe the mean's greater. In all 3 of these cases, what we're going to do is we're going to compute the standardized value, which I'll call Z0. And this is the sample mean of whatever data you're collecting, minus the mean that you're trying to test against. And in our case above, it was that 7.5 number. Okay, so you want to know whether the mean is equal to mu naught or not. And then you're going to divide by the standard deviation. But the standard deviation is going to be the population standard deviation divided by square root of n, which is an idea from chapter 7 that we talked about. Okay, so it turns out when you compute the standardized value, this is the formula that you'll use. And if you have a two-sided or a left-sided or a right-sided hypothesis test, left-tailed or right-tailed, I should say, you'll have different values to compare it to. So if you use a two-sided hypothesis and you have a significance level alpha, remember that the significance level is the probability of having a type 1 error. You can have a type 1 error in one of 2 ways for a two-sided hypothesis test. Let me go back up. You can have a type 1 error. In other words, you could be wrong by underestimating or wrong by overestimating. And your total probability, your total willingness of getting a type 1 error is going to be alpha. So that means that you have to split that over the lower half and the bottom half. And since everything about the normal distribution is symmetric, it means that you have area alpha over 2 here and alpha over 2 here. Okay, that's why these cutoffs are z sub alpha over 2. This is not a great resolution here, but this is z sub alpha over 2 and negative z sub alpha over 2, again by symmetry. If you have a one-tailed test, in other words, left-tailed or right-tailed, then you don't have to split the alpha into 2 pieces because you're only worried about whether the mean is equal to some value or whether it's less, right? So your willingness to be wrong is only going to happen on one side. Okay, so that's what's going to happen for one-tailed tests. So what this basically says for the critical value approach is you're going to compute the test statistic. You're going to determine your significance level ahead of time. And then from your significance level, you can either find your critical value if you're going to do the critical value approach, and then you want to compare these. Does your standardized value fall in the rejection region or not? And then that tells you what to do. Or equivalently, what you can do is you can compute the standardized value and then from that determine what's the p-value of that data. And we'll talk about examples on how to do both of those. Okay, so this is how hypothesis testing is going to work if the population standard deviation is known. If the population standard deviation is not known, then everything's going to be the same, except you're going to change all the sigmas to s's. You're going to change all the z's to t's. But other than that, everything will be the same. Okay, so that's really going to be the only difference. So you compute what's called the studentized value, because this is the student's t-distribution. You compare it to the critical values plus or minus t sub alpha over 2 if it's two-sided, or plus or minus t sub alpha, depending on whether it's one-sided, left-tailed, right-tailed. And then again, you can either do the critical value approach or you can do the p-value approach. Okay. And that's in general how these hypothesis tests are going to go. What we'll do in our next video, is go over a few examples of how to actually implement this in practice.